Hi everyone, this is a video of lecture 2, which I will explain section 2.2 in your course book, which is titled as Limit of a Function and Limit Laws. Let me start sharing my screen. Okay, this is the topic of lecture 2 video, Limit of a Function and Limit Laws. And as you remember in the lecture 1 video, we saw that limit arises when finding the instantaneous rate of change of a function or the tangent to a curve. Here we begin with an informal definition of a limit, and we show how we can calculate the values of limits of a given function. Okay, consider this function, for example. Here, when trying to evaluate this function at the point 2, what happens? So this function is in fact simplified. Okay, let me write it in this way. Over x minus 2. And this can be simplified so that you end up with this expression for this function. But this value, this expression gives you the values of your function when x is different than 2, right? What happens at x equals 2? This leads a division by 0, right? So f of 2 is what? F of 2, if you insert 2 to those x values, becomes 0 over 0, which is an undefined value in math. So in this situation, we explore the values of function not at this particular value x equals 2, because in this case it turns out to be undefined, but still we can explore the values of this function around this point x equals 2, right? So this is the calculated values of this expression at some different points. So for example, x equals 1, your function gets the value 3, 1.5 is evaluated as this value, and so on. You can also try to approach the value 2 from the lower values like this. For example, if x is 2.5, you get this value, 2.1, 2.01. So you see all the evaluated values here, except that x equals 2. What happens x equals 2, as we set here at the value 2, your function becomes 0 over 0, which is an undefined value. Okay, this is the algebraic computation for this particular function. And we can also try to make a geometric analysis of this function. So what we have obtained here, if x is different than 2, your function is given as x plus 2. So this is the line x plus 2, y equals x plus 2 line. And at x equals 2, what happens? Your function is not defined, but still we may interested in the values of this function around the point 2. You see, if you look at the values listed here, okay, listed here like 1, 1.5, 1.9999, it is in fact like you are approaching 2 from this direction. So you see that all the values on this graph are approaching to the value 4. And you can do the same on the other direction, like this direction here. All the values of x and the evaluated values of your function is given in this table. So if you are approaching from this direction, the values of your function approaching towards 4, like here. So this picture tells you that the values of your function f of x approach to the value 4 when the values of x is approaching to 2 from both directions. And the mathematical notation to express this behavior of your function is like that. We say that limit of your function as x approaches 2 is 4, because as you can see from the graph, all the values are approaching to the value 4. Okay, and in general, So this is the explanation for this particular function, but in general, your function may look like differently. Let's say this is the graph of your function. And okay, let's say this point is the point x0. And what happens around x0 to the values of your function? Well, this is y equals f of x. Let's say let's call this number as L. So even if your function is not defined, f of x is not defined at x0, you know, just like we have here. If you insert 2 to your function, it'll end up with division 0. So this is an undefined value. And it is also seen from the calculated values in the table. So even if your function is not defined at this particular point x0, you can still look at the values of your function around x0. You see, we never touch x0, but we may still be interested in the values of your function around this point x0. So what happens? Let's try to see. If you approach from this direction, the values of your function are approaching towards L from like this, you see? And if you approach x0 from this direction, look at what happens to the values of your function. The values of your function are going like this, but again, still approaching to this value L. So this kind of behavior of a function is denoted by the limit notation like this. You say the limit of your function as x goes to some arbitrary point x0 is this value L. And you can put this equality sign here and say the limit is L, even if your function is not defined at that particular value, okay? So after looking at this informal explanation of this limit, now we can look at the formal definition of a limit. If the value of your function f of x are close to L, just like seen here in this graph, right? This is y-axis, this is x-axis, and we see that the values of the function are really close to L when the x values are really close to x0. So if this situation happens, in other words, is the value of f of x are close to L whenever the values of x are close to x0, or you can say that whenever x approaches to x0, or whenever x goes to x0, then you say that limit of your function as x goes to x0 is the value L, okay? This is the definition of limit of a function. Okay, here you will see another particular example. This time we are interested in this function. F of x is x minus 4 divided by x minus 2, okay? And what happens f of x if you insert x equals 2? Again, you end up with a division by 0, right? And a number divided by 0 is an undefined value. So in fact, we can write this as a fact. If you divide a number, a finite number, by 0, this is always an undefined expression. So this is what happens when you try to evaluate the value of your function at x equals 2. But still, even if it is undefined at x equals 2, you can look at the values of your function around 2. Let's look at them. Okay, in this table, the x values and the evaluated values of your function at these different values of x are listed. For example, if x is 1, you got this value 1.5, 1.8, and as you can see, we choose numbers step by step that are close to 2, and you can do this from the other direction. You start with 8, 4, 3, and you get closer and closer to the point 2 from both directions. And let's see what happens to the values of x. So if you take values on this direction, if you approach 2 from this direction, you'll see the values are getting bigger and bigger, and it grows infinitely many big when you are really close to 2 from left. So in fact, this is the graph. These green curves are the graph of f of x, x minus 4, x minus 2. And you see at this direction, when you put really close values to 2, the evaluated value grows really big. So, and if you get closer and closer to 2, you will understand that the values of your function approach to plus infinity. And if you look at from this direction, then you see that the values are getting really, really small, and they grow really fast to minus infinity. And what can we say about the limit of this function? So there is no particular unique number here towards which the values are approaching. Remember the previous example here. There was a particular unique value from both directions there is a unique value towards which your function approaches. But this is not the case here. You see, on the left, your values grows too big. On the right, your values are too small, like minus infinity. So since there is no unique number towards which your function approaches, you say that limit does not exist in this case. As x goes to 2, what happens at 2? As you can see, there is no evaluated value at x equals 2, so your function is undefined. Also from the graph and also from algebraic calculations, minus 2 over 0 is an undefined value. Okay, so when we say that x approaches 2 from this direction, it means that you choose very close numbers like 1.9999. So you are looking at the values of your function at the very near numbers to 2, and you can do the same in the other direction, like you choose numbers 2.0001, which are really close to 2 from right. Okay, and this is a particular example that shows limit does not exist. What is the reason? The reason is that there is no particular finite number, unique finite number, towards which your function is approaching. Okay, another example. Here, you will see 3 different situations on which your function has a limit, but it behaves differently at the limiting value 1, okay? In all those 3 examples, we are looking at the limit of the given function as x approaches 1. All of them has limit 3. Why? Let's write to understand. In the first case, when you look at the values around 1, and if you try to see the values of your function as x is really close to 1, what happens? From this direction, the values of your function are getting closer and closer to 3. Also in the other direction, the values are getting closer and closer to 3. You see, it is so obvious from the graph. This is the graph of y equals f of x. That's why, since there is a unique number from to which your function approaches as x values are close to 1, the values are getting closer and closer to 3. There is this unique finite number. So you can say that limit of your function is 3. What happens to value of your function at 1? F of 1 is obviously defined as 3. So your function is defined, limit exists in this first case. Okay, let's look at the second graph, second case. In the second case, okay, this is our y equals f of x function. The only difference is that at the point 1, your function is not defined. When it comes to the limit, it behaves exactly the same. When you look at the values of your function as x is around 1, what happens to the values? Try to see. The values are getting closer and closer to this point 3. That's why limit exists. It is a unique number towards which the values of your function approach as x is near 1. But there is an undotted point here, empty point here, which shows that your function is undefined at x equals 1. Even if it is undefined, limits still exist, okay? And let's investigate, analyze the last case. Here, the limit, again, is 3 as you look at the values of your function y equals f of x when x is around 1. The values are getting closer and closer to this unique number 3, limit is 3. What is the difference between this case and the previous case? For example, the difference is that your function is defined now at x equals 1 as minus 2. You see, function is defined, but the defined value doesn't have to be the same value as the limit. You see, limit may still exist even if your function is defined as differently at that particular point 1. Limit is 3, while the evaluated value is minus 2 in this example. Okay, so after trying to understand what does limit mean over this 3 example, then we can try to look at the limit laws. They are so natural laws. For example, let's say limit of the function f of x is L and the limit of the function g of x is given as m. So limit operation respects addition and subtraction, meaning that you can distribute limit over sums and over differences. So evaluating the limit of a sum of a function of 2 functions is the same as evaluating limits first and then sum up the results like this. This is L, this is given as M, okay? So limit respects addition, and similarly, you can evaluate the limit of the overall difference of 2 functions like that by just distributing the limit to differences like this. So this is L, this is M, the result is L minus M. And here, K is an arbitrary constant, arbitrary real number. All the constants that does not depend on C can be taken out from the limit, and then you can still you can still continue computing the limit. So this is what? This is K times limit of f of x as x goes to C. So this is given as L. That's why the result is K times L. So this shows us what? Limit respects also scalar multiplication. And in this case, we see that limit respects multiplication of functions. So you can just distribute limit to multiplications of functions so that the result is product of the result of the limits. And similarly here, you can distribute limit over the ratios provided that the limit of the denominator function is different than 0, okay? Here M is the limit of the denominator function, and we want it to be different than 0 to distribute the limit over this ratio. And there are also these natural rules about the limit. You can take this limit operation inside this, taking the nth power operation like that. And similarly for the nth root, okay? And these are the natural limit rules that we will be using while computing limits algebraically. I stop here for the second lecture video. See you soon in the third lecture video.